Hi, in this new episode, let's discuss a new kind of game called zero sum game. Okay, so let's make the definition first. So basically, a zero sum game is a simultaneously move game, right? Or it's also called a strategic game. Okay? And where there are two players and the payoffs of the two players they sum up to zero. Okay, so that's why it's called zero sum game. Okay? So let's say a strategic game. Okay, and recall that we use a tuple to denote a strategic game, right? So it only has a number of players and the action space and the utilities, right? Okay, so n has one and two. There are two players. Okay, and AI is the action profile, and UI is the utilities. Okay. Okay, so this tuple is called a zero sum game. Okay, if u1 plus u2 is zero. Okay, so this intuitively this means that each player wants the worst result for the other player, right? For the opponent. So in that case, then the player themselves will be uh, the best, right? Has the best outcome. Okay, so now let's have a straightforward example of a zero sum game. So example, so number one and number two. Okay, so let's say each player has three actions. Player one could play up, middle, or down. Player two could play left, middle, or right. Okay. All right. So let's say the payoffs are as follows. So here's 2 and minus 2. Okay, so in each block, in each cell, we have those two numbers sum up to 0, right? So that's called zero sum game. 0, 0, and let's say 1 minus 1, 5 minus 5, minus 3, 3, 2 minus 2, 1 minus 1, minus 2, 2, minus 2, 2. Okay? All right. So remember, how do we use the method with double lines to label the Nash equilibrium for this simultaneous move game or the strategic game previously? So let's say if player 2 is playing L. Okay, all right. So in this case, player 1 is playing M, right? If player 2 is playing M, then player 1 is playing U. If player 2 is playing R, then 1 is playing M, right? Okay. And for the other, for the player 2, so if player 1 is playing U and player 2 is choosing um, M, right? And here is choosing M, and here is choosing M or R, right? Okay. And we have one pure strategy Nash equilibrium here, which is the U for player 1 and M for player 2, right? Okay. So that's the how do we use the Nash pure strategy Nash equilibrium to solve this game, okay, as the solution concept. And alternatively, we could use a theorem or the proposition for which is just for the zero sum game, and we can have the same Nash equilibrium result outcome as we did here, right? Using this approach, so they have the same result here. Okay, and we'll shortly introduce the other approach. Okay, so before that, let's formally demonstrate this result or this proposition. Okay, And for that, we need some notations. Okay. So for a zero-sum game, okay, all right. So for zero-sum game, n equals to 1 and 2, AIs and UIs, okay. So an action, all right, X star from A1. This is called a max minimizer. Max minimizer. Or maybe we can call that max minzer for short, maybe. Okay, max minimizer for player 1 if we have the follows. So if the mean of U1 given X star and some Y, okay, so this Y is from A2 and this is minimizing this U1, okay, so if that utility for player 1 after minimizing by player 2, if that is greater than or equal to minimize over Y, okay, U1 X, Y. So this X for any X from the A1, okay. So if we have this, then it means that this X star is a max minimizer for player 1, right? Okay. So what does it mean for the max minimizer? Right? So this minimizer means those operations, right? Those minimize. Okay, so this max comes from here, right? So if we have greater than or equal to, okay, and this X star always has a higher or the maximum utility for player 1 given any other X, right? Given any kind of X which is available from A1, right? So that's max, and those are the means, right? Okay. And analogously, so we have the similar definition for player 2, okay. Similarly, so Y star, okay, is a, let's simply call that max minzer, which is a short for the max minimizer. So it's a max minzer for player 2 if similarly for minimize over X of U2 X Y star greater than or equal to U2 mean of X U2, right? X Y. So this is for all Y in A2, right? Similarly. Okay, so we have those notations. Then we can have this basic property or this proposition for the zero-sum game. Okay, let's call that as a proposition. So given this game, this zero-sum game, G, okay, and includes 1 and 2, okay, AI, UI, right? So this is a zero-sum game, right? Okay, so if X star and y star. So if this action profile is a Nash equilibrium of this game G, and then x star, this action is a max minimizer or max minimizer for player one, right? And y star is a max minimizer for player two, right? Okay. All right. So how do we prove that? Okay. Basically, we use the definition of Nash equilibrium, and we use that to show that this is the payoffs for the zero sum game, right? Okay. So first, we let this action profile x star y star to be a Nash equilibrium, right? That's our start point. And what we want is to show x star and y star are both max minimizers, right? So that's our goals for this proof. Okay, so by the definition of Nash equilibrium, so what we have is, let's say for U2, x star y star has to be greater than or equal to U2 x star y for all y in the A2. Okay, so that's given by the definition of Nash equilibrium, right? So no one has incentive to unilaterally deviate from the equilibrium. Okay, so if player two deviates to some other action y, to any action y, instead of the equilibrium y star, then it has a weakly lower payoff, right, than the equilibrium payoff. Okay, so that's the definition of Nash equilibrium, and since we have definition, so this is a zero sum game, right? So we have definition for the zero sum game, which means that U2 and U1 sum up to 0, right? So U2 is minus U1. Okay, so we substitute that into the above inequality, then we have minus U1 x star y star, which is greater than or equal to minus U1 x star y, and for any y, right? Okay, so we have, then we multiply this inequality by minus 1 and then reverse this direction. So U1 x star y star, which is smaller than or equal to U1 x star y, right? And still for all y's. Okay. Since we have that it must be true, also true that U1 x star y star, it has to be less than or equal to, okay, not only U1 x star y, but also the minimum value of that, right? Because it's smaller than everything, so it has to be smaller than or equal to the minimum of that, right? So this is over y. Okay, and then again further, okay, so this thing, it has to be smaller than or equal to something else if we maximize this over x. Okay, so we have everything else the same, mean over y and u1. Okay, all right, then if we do not have the equilibrium action x star, if we have some let's say some other action x, okay, and we maximize this mean of u1 over x, then this has to be greater than or equal to the equilibrium payoff, and which is minimized over y, right? Okay, so intuitively, so from here to here, this is intuitively, this means that we are having this for having that to be true for the smallest for the minimum value of u1, right, which is led from some y, right, induced from some y to be true. Okay, so that's the intuition for the first inequality. And for the second inequality, the intuition is that for the that is actually the we do not limit to the x star, right? So we have some general x which makes this as the maximum over all those minimized u1, right? So that's those are the intuitions of those inequalities. Okay. All right. So that's one direction, right? We have put this u1 to be less or equal to this maximum u1 xy, right? If we can show the other direction, then some two things which are equal to each other, and we have something in between of those two equal things, then actually we can show that those three things are the same, right? Okay, so this is the first part. All right, no worries, and we'll show the other part and see the final result of that. Okay. So similarly, right? Similarly, again, by the definition of Nash equilibrium, okay, so u1, all right, x star, y star has to be greater than or equal to u1 x y star, and this time for all x in a1, okay. Because we want to show the others the other direction. Okay, so let's copy and paste that. Okay, so because we have this, and further we can show that this is greater than or equal to something else if we minimize u1 over y. Okay, so this could be this is true because the minimized value of u1 over y, this could be even lower or equal to the u1 xy star if the players, they are not in equilibrium, right? So this has to be true. Okay, so if we have that, then we can from this inequality together, so we know that, so u1 x star y star, this has to be greater than or equal to the max again, right? So greater than or equal to the max over x in a1 and mean over y in a2 u1 xy, right? Okay, so this again, this has to be true because if we have the u1 x star y star, which is greater than or equal to the minimum over y of the u1, right? Then if we since the above is true, right? Then what we have is that because it is true for all those values, right? Then it has to be true for any of those. So, and it is also including the one which makes this as the maximum, right, for some x. Okay, good. So All right. Then we can, what we have is from here, right, is that we can use some, okay, all right, let's use this. So we have this, right, and what we have from previously is this, right? Okay, so we can see that u1 x star y star is smaller than or equal to the max mean of u1 xy, and it is also greater than or equal to the max mean u1 xy, right? So it has to be equal to max mean u1 xy, right? Okay, so u1 x star y star has to be exactly equal to max over x and then mean over y of u1 xy, right? Okay, so that completes the proof. And further, if you want to also verify that this satisfies the definition for the zero-sum game, for the properties that is satisfied in the zero-sum game, then we can further see that. Okay, so we further note, okay, so the minimum over y u1 x star y. Okay, so from the previous proof, we can see that this is greater than or equal to u1 x, not x, what is x star y star. Okay, and we have shown that u1 x star y star is exactly the max mean, right? Okay, u1 xy, right? Okay, and again, this max mean from the proof, we know that this is greater than or equal to just the mean, right? u1 xy. Okay, so from here, you can see this is greater than or equal to this, right? And that is true for all x. And from here, this is the definition of the zero-sum game, right? Or this the it's not the definition of the zero-sum game, but it's the actually that's the right, that's also some property that we have, right, in the zero-sum game, or we can call that some sort of definition. Okay, good. All right, now let's go back to the example and verify our theoretical results. Okay, so let's find out in the example, how do we find this Nash equilibrium if we are using the proposition that is given previously here. Okay, so let's go back to the example. All right. Okay. Let's just copy and paste that and erase the previous notations. Okay. All right. So let's erase this. Okay. And this is all right. Good. Okay. All right, let's start from player one. Okay. So if player one is choosing U, okay, and what we know is that player two wants player one to have the minimum payoff in this case, which is that player two is playing M, right? So that player one is getting 0 here. So player two must choose M, and player one gets 0. Okay. So if player one chooses M, then player two, okay, so that's the first 0 here, right? Then player two is having M again, so player one is having some -3. Okay. if player 1 is playing D, then player 2 could either play M or R, both gives -2. M or R, -2, right? Okay, so that's the mean part, right? How about the max part? So after mean, then player 1 compare all those payoffs, then the max is 0. So it means that player 1 has to play U, right? Okay. And similarly for the okay, so that's the first one, right? That's the part for the player 1. Okay. How about for the player 2? If player 2 is playing L, okay, then player 1 is, let's use another color. Okay. If player 2 is choosing L, then player 1, once player 2 has the minimum payoff, then player 1 is playing N, right? To have -5 for the player 2. Okay, and if player 2 is playing M, player 1 has to play, let's see, which one is the minimum? Play U, right? So that player 2 is having 0. Okay, because 0 is less than 3 or 2. If player 2 is playing R, let's say, then player 1 must choose M, right? To let player 2 to have -2. Okay, so player 2 compares all those to make the highest payoff, which is 0, and that's when player 2 is choosing M initially, right? Okay, so we have exactly the same Nash equilibrium as we did when we were using the double underlying approach to solve the pure strategy Nash for the simultaneous move game, right? Okay, so this is the basically everything for the zero sum game, and basically each player is choosing the max sum strategy to choose the maximum over some strategy of themselves, of their own payoff, and if that payoff is already minimized by the opponent, previously, right, or just simultaneously, but which is given already, right? Okay, good.